Good afternoon. Happy Valentine's Day to all battery lovers. Welcome to everyone. My name is Johan Blondelle. I will be moderating this session together with Professor Bodoardo. And my role in the European Commission in DG RTD is to liaise with the Bat4U partnership together with my colleague Rui. Rui, stand up so that people see you. So the two of us are forming the liaison with this new partnership on batteries. But what we are going to discuss here are projects that are following from the green vehicles calls. So I think you are all aware that the Commission and Europe in general has taken the decision to phase out internal combustion engines by 2035, which means that there will be a lot of need for batteries. And we just can't use any batteries. We will need high performance, of course, because everyone wants to drive as far as possible. But we also put a lot of emphasis on having safe, reliable, and long-lasting batteries that are, on top of that, affordable for everyone. And what is becoming more and more critical, especially in the light of the recent geopolitical events, is the need for the need for sustainability and European autonomy. So there is a lot of emphasis on the sustainability of the production of the batteries, reducing the use of critical raw materials. And then in the first place, I'm thinking of cobalt, but also graphite is one of the hidden substances inside batteries that is very critical in terms of supply chain. On top of that, the circularity is very important, so we need to prepare for recyclability of the batteries as well. And the production process needs to be green as much as possible, so using green energy as little as possible and reducing all of the other emissions in the course of the production process. On top of all of that, we shouldn't forget that everything needs to be competitive, because Europe has the ambition to become the second world player in terms of production of batteries by 2025. We also have the ambition to produce 69% of the batteries for local use locally in Europe by 2025, and 89% by 2030, which means that we will need a lot of local capacity here as well. Now, the four projects that you will hear about this afternoon will all contribute to these ambitions and these activities. So you will hear about new approaches to reduce the dependency on critical raw materials, to green the production process, but also, very importantly, to understand the batteries better through modeling, because in a prediction of the behavior of the battery, we can make it safer, more reliable, more long-lasting as well. I won't take any more of the useful time of the speakers, and I would like to invite on the stage Dr. Ewald, who is going to present SUBLIME. Dr. Ewald has a PhD in mechanical engineering from Aachen. He joined FEV in 2006, and he is coordinator of SUBLIME. So you can use the remote control just to go to the next slide, and then you need to click on the title.
Yeah. Thank you. Thank you much, Johan. May I say Johan, maybe? So, yes. Yeah. Thank you much for these introductory words. Yes. So I'm also happy to be here. So after the 3 years of not being here, able to be and present results in person. So I think this is a great opportunity, and I think I would like to start right away. How much time do I have? So 20 minutes? 15 minutes? Yes. Sharp. Okay. I will try to be as concise as possible and present the project. Wait a second. Okay. I have to click on the name. Okay, so this was already one of the pitfalls here, but now it works. Yeah, very good. I would like to present the project SUBLIME here, which stands for solid-state sulfide-based lithium metal batteries for EV applications. I also have to read this because the acronym is, I think, very clear. The long term sometimes is a little difficult, but okay. So it's basically we are two people at FEV who are coordinating this. That's Seitoshi Payande. He's the expert for the solid-state batteries here, and myself. So I support him then in coordinating and in presenting these projects today here. So SUBLIME, just very simple. What is the main objective SUBLIME? We want to develop a lithium metal battery with a sulfide-based solid-state electrolyte, so it's solid-state, which helps us then potentially to reach the high energy capacity of 450 watt-hours per kilogram. That means that we have to develop innovative production techniques for this in order to make this happen, especially because of the specialties of that sulfide-based solid-state. So that would already help us to establish the European competitive in battery cell production. It features then a low cobalt cathode active material. Also, no graphites are included. So basically, these are one of these challenges that SUBLIME is addressing, as Johan has just mentioned before. And this project has started in May 2020. So it's part of the BET1 cluster, where other projects, I think, presented already last year here at this conference. But we are a little bit behind this. We started 5 minutes later and will be then, according to the plan, at least April next year. You see all the partners here, so quite a cross-section through all these European partners. So OEMs also then are represented here from Ford, from Turkey. One of the other objectives, I think I mentioned already, the high rank objective of the high energy capacity, especially also with the usage of let's say more uncritical materials in terms of the supply chain, are the two pathways. So we have a high energy and a high power density path chain. It should address low costs. Due to the fact that it's a solid state electrolyte, so no liquid electrolytes are included. We address the objective of safe batteries, the sustainability, because we are using very low cobalt cathode electrode, also very high recyclability, and we, as you can imagine, of course, try to address BEV applications. So the project itself in a nutshell, so what the technology is concerned, you see here basically it starts with the 4 steps that you see in the middle. So sourcing the materials and the optimization of those ones is important. The production, so start from very small coin cells to upscale them at kilogram scales, where we can manufacture larger pouch cells as depicted in this picture here. Exemplarily is, I think, the objective, of course, and then the testing will become important, especially also to prove that we reach the performance and also have the inherent safety there. What's very important is the development of this in the upscaling of the sulfidic solid electrolyte with a very high ionic connectivity, and the corresponding development of both the positive and negative electrode. So and the upscale of the production of those ones. We produce basically the plus electrodes, the cathode, here within the project. For the negative electrode, we source lithium copper foils from an external supplier. I think that's important to say because this is also one of the things, one of the challenges at the end of the project here, which I would show to you. And all that has to be put into a kind of a whole technology package, because we have to develop the casted electrodes, then later for the upscaling of in pouch cells, the processing routes, that all needs to be optimized, that we have the right cyclability and the energy density. So in order also to avoid lithium dendrite formation, so major attention is being paid here on the development of these protective layer strategies on the anode side. So what we will have at the end are monolayer pouch cells of this size, 1 to 10 ampere hour cells, and testing will also come, and then I think next time I will be able to show more about the results here. So let's start directly with the results here. You saw the technobricks on the previous slide. What SUBLIME so far has achieved, we have the solid state sulfuric electrolyte, so that's an agrodye type material that we have synthesized with the needed ionic connectivity that we need, and the size distribution and the purity that we want to have. So this is one of the first things that we had available, and now we look how this then just works together with the other technology bricks. So we also have an NMC here. It's a low cobalt NMC, NMC 811, which is being optimized and to work together with our solid electrolyte, which is working well. It shows also basically on a coin cell already that we are coming close to the actual capacity that we are targeting at, the main target. So you see it's still work in progress, is 210 milliampere per gram, but we are already very close in seeing how this works together with our coin cells here that we use in SUBLIME for the materials, that we are come very close already to the performance here and can proceed further with the upscaling, that we have enough material for the testing. So this is one of the things. Then we go further. We have seen now the electrolyte, we have seen the cathode. We work on the anode material. As I already said before, the anode material is being sourced outside of the project. It was not objective of SUBLIME, also not in the cost range that we could manufacture and develop this by our own. So we used suppliers also from the Asian market, and we're testing these. We are doing testing. We are doing tests of these, and we have different materials available. And this is something where we found the first challenges. For example, the first material, which in principle we need in order to really reach the very high energy densities that we are targeting at. That's very thin lithium on copper. That seems to be kind of low quality at the moment. So cycling of these things, especially also with the development and the purification of the protective layers, showed us that we, at the moment, not yet with that material are able to cycle as many times as we like. You see here these diagrams of charge and discharge, and you see this is then at the end then very quickly destroying the cell. If we use different kinds of materials with thicker lithium, we see that our approach actually is going to work, so we can cycle quite a lot of times. But however, these are thicker lithium cells, thicker lithium anodes of which then at the end we don't need, because that's not much. There is not enough active. There is even more material than we need for active material, and that's the reason why we have to develop here a little bit more on this technology brick. But we see in principle that our SUBLIME approach works, but of course there is some more optimization needed. So while we are still further optimizing on the coin cell level the electrode, on the anode side, we can then further proceed with working towards the pouch cells with regards to the solid electrolyte and the cathode processing. So this is also then being done and it's working. We see already here that we are able to reach a very decent initial discharge capacity of that one. Maybe you remember that I showed 195 milliampere gram of active material before, so that's just slightly below this. So next technology big, we can further optimize. So this is working. However, of course, because of, let's say, the challenges that we see here on the anode side, we are using an intermediate step, exchanging lithium intermediately against lithium-indium in order to be able to continue on the optimization here. And once then we have done that, then we would come back to the lithium. I will show this. So it needs further improvements, of course, but I think this is the way that we can do, and we are still 1 year ahead of us, so there will be still enough time to do the optimization here. Next step is in terms of the parallelization of these activities between the cathode and the solid electrolyte on the one side, and the anode. We continue on the development of the protective layer for the anodes. So we had investigated 3 different approaches, and we will then still use those of one's 2 approaches under further development. You see here the SLAALD method, the so-called also the thermal evaporation technique, which we will use in order to further develop our protective layer for the anode. Maybe also we will look at using one of these 2 approaches, then at a different concept, how to protect the dendrite formation between the anode and the solid-state electrolyte. And once this is done, then we merge again with the developments of a solid-state electrolyte and the cathode in the lithium metal anode at the end. So this is basically the way how we want to do this. So Now, I would like to come basically to the conclusions of this project. We see in terms of the mid to long-term impacts, we think that of course, we have some problems in order to source the correct material for the anode side at the moment. So we have to use the thicker material for the lithium. That would mean that we would target then with that material only first to lower energy density. And once we have resolved the problems, then with the thinner and the optimized lithium copper metal anode, again, we would be able then to reach the high energy capacity. What we also see in terms of the technology readiness, I think there are also some challenges I will talk to later through. The thing, of course, the production process still needs to be upscaled, so this is very clear we can do this. It's ongoing for the solid-state electrolyte and the cathode, and we will test these on 1 ampere level cells. However, one of the challenges is that the sourcing of the decent material for the anode is definitely the problem here. Right now, we have to source these materials from Asia, and we need to have European manufacturing suppliers then, in fact. So this is in progress, I know this, but materials also then, when it comes here from European manufacturing suppliers, they are really expensive still, so that needs to be upscaled then to make it more, make it cheaper. Yeah. So sulfuric solid-state electrolyte technology, however, needs also specifically dedicated large-scale production environment. So during the production of and the working with the solid state electrolyte on sulfuric basis, there is the risk of H2S formation when it comes into contact with the vapor, water vapor in the air. So this needs to be taken care. It's also kind of aggressive, so you would really do all these processing then in a specific environment, protected against, so with a very low dew point, protected against the water vapor, and also of course, you would not like to spoil your regular production equipment for that material. So this is definitely something where it comes then to industry investment. So at the end, what would be then the cost impact for the SUBLIME technology? We will be doing at the end of the project a quite detailed recap of the cost impact. So the initial estimations at the beginning of the project were, you see here the numbers, how we think that they will drop down. Of course, we have to look at the development of the costs for the materials again. We will revisit this then at the end, as at month 48, as I say. What the recycling path is concerned, we already did some initial studies in which we concluded that we think that we really can recycle 90% of the materials. And another outlook beyond SUBLIME, just here some kind of a demonstrator, how such a automotive applications cell of 40 ampere hours could look like. So this was being designed by our partner Saft. So Saft itself, they are not completely in the automotive business, so that's the reason why the formats might look a little bit odd, but this is in principle here how we think that a pouch cell of that size would look like. So with other partners, maybe we would have a little bit longer cells. Here you see the electrode side is just a 150 millimeters times about 60 millimeters. Could also, or let's say here the pouch side, 190 times 90. Maybe we can also make it with some other materials a little bit longer. And that would in principle be what SUBLIME, that would be the next steps then of SUBLIME. Yeah. Okay, so this is it. I don't know how many, was I in the 15 minutes still, or?
48 seconds left.
Oh, okay. So what do you want to know? Yeah. So yeah, I'm really happy to be the coordinator of this project. Definitely, I can say this. I came from, as I say, I'm one of the mechanical engineers that was alluded to in the very beginning of the, and by some coincidence, yeah, I had the chance to coordinate this project, and I'm really happy to be part of it. I can definitely say this.
Great. Thank you very much. Thank you very much. I remind you that we will be taking questions and answers in the second half of the session. So please take note of your questions for the second part.
Okay.
I would like to invite on stage now Dr. Simon Clark, who is a battery research scientist at SINTEF in I never know how to pronounce it.
Trondheim.
Trondheim?
Yeah,
Okay. In
you go
Norway?
Old school and say Nidaros, how it was during Viking times.
Oh, okay, good.
So before you make the same mistake than I did, you just have to go to the Hydra and double click on
And
it.
he will present us the project Hydra.
Okay. Thank you very much for the introduction, and thank you for the invitation to speak today. My name is Simon Clark. I'm from SINTEF in Trondheim, Norway, and the coordinator of the EU project Hydra, which is developing next-generation batteries for electric vehicles. And I hope by the end of my presentation, you'll have an idea of what we're doing, how we're doing it, and where we go from here. So Hydra is developing next-generation batteries with a specific focus on hybrid electrodes for generation 3B lithium-ion batteries. And that means high-capacity silicon graphite anode blends and high-voltage LNMO cathodes. We're a 4-year project that will go until August of 2024. So as of now, we're a little bit past halfway. And we have an excellent consortium that spans Europe. It includes research institutes like SINTEF, universities, and industry partners. And our goal there is not only to take a holistic approach developing next generation batteries, but also to provide opportunities to train the next generation of up-and-coming battery scientists and researchers. So we want to develop hybrid materials. We want to develop hybrid electrode structures. Why? We're aiming that this should help enable next generation batteries in the electric vehicles market, which means batteries with high energy density, with low cost, fast charging, and good cycle life. But we also have to be kind of smart about how we approach this. We can't just get something that ticks off the technical KPIs. We also have to think about the bigger picture, right? We need to think about reducing critical raw materials dependencies by developing cobalt-free electrode materials. We need to think about the environmental and ecological sustainability of batteries, right? There's battery gigafactories popping up all over Europe now, and we need to make sure that that production is sustainable. We need to enhance manufacturing processes, that what we develop isn't just for 1 or 2 cells in the lab, but can actually be scaled to produce billions and billions of cells in gigafactory settings. And we need to ensure fast commercial implementation of the results, right? This is a fast-growing industry, and we need to get results out of the lab and into the factory. So that's what we want to do. How are we going to do it? Well, Hydra takes a multi-headed approach. See what we did there? To develop the next generation of batteries. And those heads kind of focus on 4 main topics. One is model-based design, to try to improve our understanding of what's going into the batteries and get a better idea of how we can operate them for longer lifetime. Developing hybrid materials that allow us to achieve higher capacities and more stable operation than is possible with traditional materials. Advanced manufacturing, specifically trying to move away from using NMP in the cathode processing, which, if you're not familiar, is an organic solvent that takes a lot of effort to capture and can be harmful for your health and flammable. So we're trying to move away from that to water-based processing. And we want to improve the sustainability of batteries by reducing the energy required to manufacture them. So, as I mentioned, we're now about halfway through the project, and we have a few results that are interesting to highlight. The first is that we've made the first generation of pouch cells in Hydra, not in coin cell format for labs, not in like small formats, but in multi-layer pouch cells, which would be representative of what you'd actually see in electric vehicles. And those are currently undergoing testing at the DLR. This is actually one in his hand right there. We've done a public release of a powerful open source battery modeling framework to try to help both scientists and engineers better understand and design their cells. We've demonstrated the aqueous cathode processing using water-based methods instead of organic solvents. And we've developed standards for characterization of hybrid electrode materials. And I would like to go through and highlight each one of these, but unfortunately we just don't have time today. So I've chosen to highlight this one, our open source battery modeling framework, because this is something that exists today. I'll show you a QR code. You can download it. You can use it. It's something that can be of immediate value for the community. So our modeling tool is called the Battery Modeling Toolbox, or BATMO for short. And this is an open source continuum modeling framework for MATLAB and Julia. And the thing that we really excel at in this implementation is doing fully coupled electrochemical thermal simulations, even on very large and complex geometries like cylindrical cells. For example, what I show here is an example of a 4680 cylindrical cell mesh. If you follow, I'm sure you do, the EV news, this is the design that Tesla is using in their cars. And traditionally, this has been really difficult to simulate in 3D because it's a lot of cells. You have to mesh each electrode layer very finely, and compared to the overall size of the battery, it can be difficult to solve. But we've implemented a way to do this, and for 4680 cylindrical cells, for the blade type of prismatic cells that the companies like BYD favor, we can do this. And it's also very fast. So what we've developed is free and open source, and we aim to make this not only work well on its own, but to be interoperable with other tools. We work in MATLAB, we work in Julia, not everybody does. Some people like Python. And we're trying to make it possible that if you want to simulate the same set of parameters in PyBAM or in CityMod or in another battery modeling framework, you can do that easily without having to do a whole lot of recoding. But also a lot of battery developers aren't really comfortable coding at all. So we're working on a web-based GUI where you can go in and kind of play with the sliders, play with the knobs, set up your own simulation, and view the results. So doing these kinds of simulations allow battery scientists and engineers to simulate dynamic, spatially resolved profiles for things like temperature, as we see here, concentrations, electric potential and current. And for scientists, this means that we can help guide battery design optimizations and do virtual testing. For engineers, you can better understand the performance of your cells under different conditions. And as I mentioned, this is available now. The beta release at that QR code is on GitHub. And currently it's using a command line interface, but as I mentioned, we're developing this web-based GUI for non-developers to use as well. So we've also been working on trying to improve standards for battery research and dissemination of data in the community. We heard earlier today, right, that sharing data from research is becoming a very important topic. But before we can do that, one thing that we try to focus on is improving standardization and improving results within our projects. I don't know how many people here have ever built a battery by hand, but you've probably seen some of these baking shows, right? Like the Great British Bake Off, where they give 10 bakers the same recipe, and you normally get 10 different cakes. Same kind of thing, right? In battery cell manufacturing, a lot of it is, especially on lab scale, is subject to the preferences and the prejudices of the person who built it. So at the start of the project, we did a round robin and saw that we had some reproducibility issues, and came together and wrote a set of standards for how to build cells and how to do the characterizations. And after standardization, we were able to get reproducible results. But getting reproducible results is only one side of the coin. The other side of the coin is after, okay, we have our results, how do we share them? How do we make them available to people in the community? And here we're collaborating with the Battery 2030 Plus initiative and the project Big Map, who have done a lot of really good work on supporting infrastructure for semantic data interoperability. And so in Hydra, our public data sets are following those standards that allow for semantically annotated data, both internally within the project and externally. And our goal is that this should contribute to an ecosystem for battery data that is searchable. And what we see here in the GIF is being able to search not only by strings, but by semantic concepts. We're hoping to interface this with a ChatGPT-like model so that you don't have to write your own Sparkle queries. You don't have to worry about, JSONs or turtles or OWL or all of these obscure file formats. You can write your query in ChatGPT, or in a ChatGPT-like interface, translates it to a Sparkle query, and queries the knowledge graph to find data that you're interested in. So I've highlighted that we have benefited from cross-project collaborations, in that case with Big Map and Battery 2030, especially with regards to things like standards and data and digitalization. But we're also part of the LCBAT5 cluster, together with the projects Sense, Cobra, and 3Believe, and Sense will actually be the next talk up here today. And we've been promoting joint workshops. We've had 2 already. Hopefully we'll have more in the future. And dissemination activities. So we try to live up to our motto that teamwork makes the dream work. So finally, okay, why are we doing this? We've developed some nice modeling tools. We've talked a lot about new battery materials. And, we don't do it because it's fun, even though it is, and we don't do it because it's scientifically interesting, even though it is. We do it because it makes business sense and it helps the industry, right? The model-based design tools that we're developing lead to shorter development times, longer lifetime, and less scrap during the battery production process, which ultimately means lower cost. Hybrid materials allow us to design cells and operate cells at greater energy density and for a longer time. And that allows us to broaden the end-use applications and have greater performance end uses. Our advanced manufacturing methods will lower the energy requirements, and that means fewer materials, less waste, lower cost, and greater industrial competitiveness. And sustainability means fewer critical raw materials uses and avoidance of hazardous materials and low carbon footprints. So from a technical point of view, this is kind of the impact that we're targeting. And if we look at it from a more holistic approach, there's a lot of benefits, technical, economic, societal, all around. But one that I really want to highlight is this one, skills. We are trying to facilitate the training of new battery researchers, of new battery scientists. And we have a program to do that, not only within our consortium, but also students from around Europe. That's called Access Hydra. And if you visit our website, I'll show the link in a minute. If you have students at your institutes or early career researchers who would like to do a stay at one of the Hydra partner institutes and learn a little bit more about what we're doing hands-on, then we offer opportunities to do that. So you can come visit us in Trondheim and see the northern lights or the midnight sun, depending on what time of year you come, and learn a little bit more hands-on about what we're doing in Hydra. So you can find out more at our website, h2020hydra.eu. You can contact me directly. And finally, I'd like to thank all of our partners, and especially the European Union, for funding our work. RTR, in this case, means Road Transport Research, but to me it means ready to roll. So let's do it. Thank you very much.
Brilliant, thanks very much. Then I would like to invite the next speaker on stage, Dr. Kühnel, who has degrees in chemistry and business chemistry, has a PhD at the Battery Research Center at the University of Münster, and he is coordinating the SENSE project, which is part of the same cluster as the one we just heard. So the floor is yours.
If I manage to open the presentation.
You click on the link. Yeah, that's it.
All right. Yeah, thank you very much for giving me the opportunity to present the SENSE project here today. I mean, I apologize in the beginning, my English is not as good as that of my American colleague Simon, who just presented. I'm a a scientist at EMPA. EMPA is the Swiss Federal Laboratories for Material Science and Technology. We are located in the Zurich area in Switzerland. And as Simon already mentioned, our project is also part of the LCBAT 5 family of projects. Here's a short overview of the project and the consortium. So we also started in 2020, slightly before the Hydra project, already in February. We are 11 partners from mostly Central Europe and also Northern Europe. And in terms of objectives and so on, the objectives are of course very similar. On the cell level, we have very ambitious objectives that we got from the call. The energy density, 750 watt-hours per liters, I think is one of the more achievable objectives. Fast charging capability, because we are also targeting automotive applications. A reduction of critical materials of at least 20%, and I think probably the most challenging objective is really the cycle life requirement of 2000 deep cycles, considering the cell chemistry that we are dealing with here. So generation 3B basically means silicon graphite on the anode side with a relatively high silicon content of at least 10%. And then on the cathode side, we decided to go for nickel-rich NMC. Some of the other projects rather use LNMO, for example, so a high voltage cathode material. We chose nickel-rich NMC also because it's of quite high interest from the automotive industry. In terms of topics that we're working on, we have quite a strong focus on active materials in this project, or let's say in general on materials development, active materials, also safe liquid electrolytes. But as the name of our project already implies, we are also looking into sensors, in our case in-cell sensors that we're implementing into pouch cells. So here you can actually see the first generation demonstrator with multiple sensors inside, and this is the cable that we use to access the sensor data. I think, Johan, you mentioned that in the beginning, that the green production is becoming also more and more important. So we are also looking into aqueous electrode processing, both for the anode and the cathode, and this is quite a challenge for nickel-rich NMC, as you probably heard about. And then in the end, we are also integrating all the technologies we are developing in multiple prototypes, 10 ampere-hour pouch cells, 2 generations that incorporate the sensors that we are developing, and also 2 generations of modules. The second module will have 12 of those pouch cells and a battery management system that makes use of the sensor data. Now I would like to highlight 4 results that so far came out of the project, starting with the cathode material. So here for nickel-rich NMC, the challenge is really when you increase the nickel content, you gain in capacity, which is nice, so in that way you can increase the energy density. But at the same time, the material becomes less stable. For us, the starting point was NMC 811, so already quite a high nickel content. But then we wanted to go beyond, also in order to decrease the cobalt content, which is one of these critical materials that was mentioned already earlier. So what we did here, and all these materials with these different compositions were synthesized with the same reactor. They all have similar properties in terms of particle size, in terms of morphology, in terms of surface area, which is important to be able to really compare the properties of these materials. And here in this example, we went for NMC 955, so we reduced the cobalt content by 50%. And as you can see here, if we compare here in gray NMC 811 with NMC 955, this really comes at a quite significant penalty in terms of cycling stability. So we are exploring, or we have been exploring different approaches to improve the cycling stability, including dopings and coatings, and also working on the electrolyte. And in this example that was published last year in Advanced Energy Materials, we try to substitute some of the manganese by magnesium. And what is quite interesting, when you substitute when you put 2% magnesium inside the material, you end up with a material that has a comparable or even slightly better cycling stability. Here in dark blue, if you compare to NMC 811, slightly better cycling stability than NMC 811, is similar initial capacity, while we are reducing the cobalt content by 50%, which is really important, right? And at the moment, we are upscaling NMC materials for the second generation prototype. So this is a work of our partner ZSW that is doing the upscaling. The second example I would like to highlight today is about an electrolyte that we developed in the project. So state-of-the-art liquid electrolytes for lithium-ion batteries are based on these carbonate solvents, and especially the linear carbonates are highly flammable. So we were looking for strategies to reduce the flammability of the electrolyte in order to improve the safety of the battery. And there are, of course, multiple approaches, but many of the existing approaches come at the cost of very high viscosity, meaning very low conductivity of the electrolyte, which is then detrimental for the power performance of the cell. So we explored multiple approaches in this project, and one approach that turned out to be quite successful is the use of flame retardants, because when we add flame retardants, we don't have to add that much, so the penalty in terms of conductivity is not that large as compared to some other approaches. And particularly this cyclotriphosphazine-based flame retardant is quite promising, because we just have to add 5% to really significantly reduce the flammability of the electrolyte when combining it with a higher lithium salt concentration. And there were even additional benefits that we found of using this flame retardant. It also improves the wetting properties of the electrolyte. So this compound wets cell guard separators very well instantaneously, basically. And maybe most interestingly, it also helps to stabilize silicon-based anodes, which is the largest challenge of all these LCBAT5 projects, I would say, to stabilize these silicon materials that undergo a huge volume change during cycling. And as you can see here, in that case, a silicon oxide graphite anode coupled with NMC, with a high NMC content, and high nickel content also, we can really improve the cycling stability compared to a state-of-the-art electrolyte containing 10% FeC, which is another additive that is well known to stabilize silicon anodes. We also looked into the stabilization mechanism. I cannot go into the details now, and I think the paper will be out maybe latest in a few months. It's under review at the moment. Next highlight I would like to briefly discuss is, I mentioned before, fast charging is important. And one of the bottlenecks here is really the heat that is generated. I mean, Simon already showed also the simulation results where you could see that the cells can get really hot, especially in the inside. And the larger the cell, the higher the inner temperature that is reached inside the cell. And our approach here is to reduce the electrical resistance of the electrodes, because that's a major contributor to the heat generation inside the cell. And here we are working with the company Huntsman that has a very nice material called Miralon pulp that is an alternative conductive additive for electrodes. And when we add this additive in rather low quantities to the electrodes, around 0.5 to 1% of this material, we can significantly improve the electrical as well as thermal conductivity of the electrodes. And this has kind of a dual benefit, because we are on the one hand are generating now less heat because the ohmic resistance of the electrode is lower. So if we fast charge or discharge the cell, we generate less heat. And at the same time, it becomes easier to dissipate the heat using this material. And it has a quite interesting morphology. So it's a CNT-like, so carbon nanotube-like material that wraps itself around the active material particles. And we are at the moment investigating really how the use of this conductive additive benefits the thermal properties on the cell and even pack level. The last example I would like to highlight today, I already mentioned that we're also working on in-cell sensors, and here our partner Coventry University from the UK has a lead, and they published 2 nice papers in this project where they investigated multiple reference electrodes. So we are not only interested in the temperature distribution in the cell, but also in the individual electrode potentials, which is particularly important to learn more about the state of health of the silicon-based anode, and also for fast charging, because we want to avoid states of the cell where it comes to lithium plating, right? Lithium plating meaning that the potential of the anode would drop below the lithium plating potential, and that's kind of the state you want to avoid. And if you have a reference electrode inside, you can really monitor the electrode potentials individually for the anode and the cathode. And it turned out that both gold and titanium dioxide are quite promising candidates, because these reference electrode materials offer long-term stability in the cell and also don't require a pre-lithiation step that is needed for some other reference electrode materials. And as I mentioned before, the first pouch cell demonstrator that we produced last year incorporates temperature probes and also titanium dioxide based reference electrode. And at the moment, we are working on fast charging algorithms that make use of these sensor data. As Simon already highlighted, the 4 projects teamed up in what we call the LCBUT 5 cluster, which has been, I think, quite successful. We publish a joint newsletter. You can sign up for it if you're interested. We organized multiple workshops. Last year, we organized 2 workshops on silicon-based batteries, one in Sweden, one in Switzerland. We organized joint conference sessions, for example, at the EU Green Week, the Swiss Battery Days, and the Transport Research Arena. And we also teamed up to write a follow-up proposal that has been funded last year, and now we have the Intelligent project, which is one of the first Horizon Europe, right? Horizon Europe projects. Yes, coming to my last slide. I mean, the impact of the project. I think one of the most immediate impacts, of course, is really the training aspect. That we counted a bit the PhD students and postdocs, and so far it has been around 15 PhD students and postdocs that have been employed through the SENSE project and trained by the SENSE project. And many of those people are now getting hired by different battery companies, which I think is really important for Europe, and one of the main benefits of these European projects. But of course, there's also a lot of learning going on at the companies. Not all companies that we have in the consortium are already big players in the battery industry. So we can really see that our project is also helping companies to enter the battery market. So they're now a step closer to enter the battery market. And I think this is also what the Commission is hoping for, right? Really a highlight for us was my first highlight to show that it's possible to reduce the cobalt content significantly in these nickel-rich NMC materials while maintaining a good cycling stability. This goes into the environmental factor and into Europe's dependence from critical raw materials. And yeah, I already mentioned that we have this follow-up project. I think further follow-up projects are in the pipeline. And we also have partners that are really close to commercializing technology that we've been developing here in the project at a relevant scale. So that's also really nice. Yeah, with that, I would like to thank all the project partners, thank the organizers, thank the European Commission, European Union for the funding, and thank you very much for your interest. Thank you.
Thank you very much. And now that brings us to the final speaker of this session, Dr. Petit. He has a degree. I set the timer, so you were perfectly on time. Oh, well. Perfect. So he has a degree in chemical engineering from INP Lorraine. He joined IFP Énergie Nouvelle in 2012, and he is going to present us the project Modalis.
Thank you very much for the introduction. Thank you very much for attending this talk. So I will present you the results, main results of Modalis project, as stated. So for the first presentation that you had today, they are focusing on creating the materials and batteries for the next generations. But as you have been able to see, there are many challenges that are created by these new technologies in terms of new materials, new behavior that needs to be understood, and that's the main goal of the Modalis project. This project is H2020 project from LCBAT 6, not LCBAT 5 that we saw earlier. It began January 2020, and the duration, it will last until August this year. So we are the final part of this project. And in this project, we gather a lot of 10 partners from the industry, for battery manufacturer, car manufacturers, material manufacturers, as well as software developers with Siemens, and academics. So the aim, as we saw, there are a lot of challenges that are created by the new technologies for batteries, especially for Gen 3B and Gen 4 batteries. And this needs to have some new tools in order to model them and to understand their behavior. So this will help all stakeholders from the battery industry in order to create better materials, better products. So material manufacturers will be able to evaluate, thanks to this model, the material performances into future battery cells. Battery manufacturers will be able to adapt their processes, their designs with the new materials in order to have optimized cells and make sure that they are working according to the best quality that the material manufacturers have created during their development process. And OEM and end user will need to know how the batteries are working in order to implement them and use them correctly into their products. So in order to answer these needs, we want to create in Modalis project a modeling toolchain that will be able to tackle the new behaviors that are created by this next generation batteries, generation 3B batteries, like what was presented by Sense Project and Hydra, by Simon and Ruben, regarding especially the silicon anodes and NMC, low cobalt NMC positive electrodes, and especially with the silicon anodes tackling the high volumetric expansion, which will create mechanical damage to the electrode, and take that into account from the material to the cell or module level. And for Gen 4 batteries, we are using new type of electrolytes, solid-state electrolytes, so the conduction of ionic conduction into this electrolyte needs to be taken into account. And then you have plenty of new interfaces to play with, especially solid-state interface, with the positive electrode, with the negative electrode, and inside the electrolyte itself. So all these new interfaces need to be taken into account in order to understand the behavior and the challenges of this material to implement them correctly into final systems. So to do that, we are based on a multi-physics, multi-skill consortium, going from the material to the prototype scale, using skills from the industry in order to better know what are the challenges according to industry partners, and also from public research innovation actors, and also multi-physics, gathering physico-chemical characterization, mechanical behavior, thermal behavior, and of course electrical and electrochemistry. So still some mechanical engineering, but mostly a lot of other skills needed for this. So for the main results that I would like to present you today, we have, as I said, we are going into the last part of the project, so we are still 6 months into the project before the end of it. So we are finishing the work on the Gen 3B cells, and this led to the development of a multi-scale and multi-physics toolchain, going from the material with DFT modeling of silicon oxide, graphite, and also NMC, in order to get some specific material properties at this level that are then implemented into particle scale modeling. So this is very specific to our application because we have very specific particles, especially for the negative electrode, with inclusion of silicon into a silica matrix, and this led to a specific behavior of the particles that needed to be taken into account. These particles, once they were modeled, were put into an electrode, to an electrode scale modeling, where we were able to study the mechanical behavior of the electrode. Then this gave us some information how the electrode works in order to implement it into a full 1D cell behavior model. In this case, we were able to study the aging, safety of the battery, based on the mechanical properties and electrochemical properties of the material. And finally, it was implemented into a 3D model by Siemens in order to evaluate the heterogeneity behavior into the battery and see whether we have some heterogeneity, especially regarding the aging of the battery. So usually when we have modeling, it's quite the easy part because when you put parameters, equation, everything together, it works. But if you want to validate this, you need to have specific materials to do experiments and see whether your model is relevant or not with this material. So that was a very big, difficult part for this, in order to create some specific batteries that are representative of future industrial batteries. So the main difficulty here is future, because you don't have actually then 3B cells that are on the shelf that you can buy. So we had to get some material, create the cells. So Saft created some cells that were relevant for our project. So it was NMC811 silicon oxide graphite cells. And we wanted to have a huge impact of silicon, so we aimed at 20% of silicon into the negative electrode. So 20% was a way for us to ensure that we had sufficient volumetric expansion at the electrode level and see the impact of mechanical behavior on the electrode. We resulted with 5 ampere-hour cells, so it was less than expected, but due to technical challenges, it was a good result to get these cells and make them work. So they were put into these jigs, and we created, we made a test campaign on these cells in order to evaluate the aging, the nominal behavior, of course, and the safety of the cells. So you can see here, for instance, we did set at cell level. Of course, we had also specific measurements done on the material level with TEM and SCM analysis to understand the way the material was working into the cell, and also did some specific dilatometry tests in order to understand what is the mechanical behavior at the electrode level with an electrochemical dilatometer, and also at the cell level where a specific cell dilatometer was developed by Siemens CT in order to evaluate, to see the behavior of the cell during cycling. So the good thing with this cell is that it's aged very fast, so we can see very fast the behavior of the cell in terms of aging, and get faster also behavior, aging behavior, in order to calibrate the models. So the multi-scale modeling, as I said, was done at multi-scale. First, at the molecular level, we are able to get the transport and mechanical properties of the materials, especially for the NMC, the diffusion parameters of the NMC, and the mechanical properties of the silicon. Because as we bought some commercial material with silicon coupled with graphite, it was not possible for us to separate silicon and graphite and analyze them separately. So we had to guess the material behavior from DFT calculations. Then at the particle scale, as I said, we had realistic behavior of the particles, and we were able to compute the stress generated into the particles due to the swelling of the materials. And of course, the swelling of the particles, as we can see here, were also evaluated thanks to this FEM simulation. At the electrode level, we did a mechanical behavior of the electrode thanks to discrete element modeling. As we see here, the aim of this modeling is to see what was the swelling of the electrode during cycling, and also monitor the bond damages in order to evaluate how much active material was lost during cycling due to mechanical failure. And finally, at cell level, the cell nominal behavior, including safety, was evaluated thanks to the models, and also thanks to using Siemens SimCenter tools, we are able to do also a 3D modeling of the cell in order to monitor the heterogeneities. So once we finish this first toolchain at the Gen 3B, we switch directly to Gen 4, just not to be too much bored with our results. And we did the same kind of approach with the material from Gen 4 batteries. First, with ab initio modeling, we focused on the behavior of electrolytes in order to evaluate the conductivity of these electrolytes, as well as the behavior of the interface, especially focusing on lithium-indium electrolyte interface. Then we switched to mesoscopic behavior in order to understand the behavior of electrodes. On one side, the NMC solid electrolyte behavior with the positive solid electrolyte interface, and at the negative solid electrolyte interface with specifically phase field modeling in order to understand dendritic growth at the negative interface. Then, using 1D simulation, we wanted to evaluate the behavior of several types of solid electrolytes on the behavior, check whether the models we used for liquid ionic conductivity were still valid for solid ionic conductivity, and also implement the influence of pressure on the overvoltage in the cell. And finally, even though we will not have some experimental push cell in our project, we will upscale the behavior that we will monitor, we'll see on pressure cell up to 3D push cell in order to evaluate the behavior of this large-scale cell and see the main challenges that we will face when we want to create real push cell of high ampere hour, with a high number of ampere hour. So as for Gen 3B, we have dedicated cell characterization for Gen 4 using pressure cells. So the reference material we use is hydrodite. We will have 3 types of hydrodite, a nominal one that we are using currently, then a second one with a smaller granulometry, and a third one with better performances in order for our colleagues from DFT and ab initio calculation to see whether they are able to simulate the change in electrolyte formulation with their models and understand the new behavior that we can monitor experimentally. Finally, we have built we served complete cell in order to study the whole system together with NMC811 hydrodite and lithium-indium, and also symmetric cell in order to specifically study the behavior of the negative electrolyte interface. So the mid to long-term expected impact is to help the stakeholders with new knowledge on the behavior of next-generation batteries in order for material manufacturers to help to sell the material and to show the benefits of the material at the full system level. Then for cell manufacturers, assess the new generation cell performances in new material performances into cells and optimize their design in order to make sure that they are used properly and are able to be optimized at the cell level. And finally, for OEM, make sure that they are able to correctly use the new cells and the next generations into their systems, especially when we have a lot of effect due to the mechanical properties. Make sure that the mechanical design of the battery pack or module are fit with the new battery behavior. So finally, we will be able to optimize the cell development all along the value chain from material manufacturer to OEM, and better integrate the material into cell for accounting for the relevant properties, the material properties, the design properties, and also the numerical properties. These new tools are relevant for the next generation batteries, especially Gen 3B with high silicon content, which could come into the market in 2025, and Gen 4 batteries with electrolyte, which could come to market in 2030. So thank you for your interest.
Okay, thank you very much. Now it's time for the Q&A session. I just ask you to speak in the microphone that I guess it will be provided, because there are also people that are attending online, so it's very important that they can follow the questions. When you just introduce yourself with a name, your name and affiliation, and please tell at which project is addressed your question. And please, the floor is open for any question you can have. I guess there will be many questions because the projects were very interested and the presentation was very high level. So please, Wouter first, because that's the only one raising his hands to start. Don't be shy. Thank you, Wouter.
So, hello, my name is Wouter IJzermans. I'm the Executive Director of BEPA, so the private side counterpart of Johan in the BAT4EU partnership. So very interested in the results of the project here, and there are many good ones. Just one remark for Simon. I saw you had some really good cross-project collaboration. If you could rename them synergies, that would be easier to find when the Commission does Control F in the search results. But for all of them, I was really also impressed how forward-looking your projects were in terms of upscaling and making already industrial prototypes or thinking about them, or either thinking about future projects, what Ruben was saying. So do you have some lessons to share there? Because you're all sort of seeing the finish line, like how you will put this results forward into next projects. Are you looking for commercial exploitation or for new research projects? What's your approach on this? Just for all of them.
Okay. So you want to start in the order you spoke, maybe? Just to answer, maybe.
Does it work now? So, okay, I have to press the button, yes. I think it came out clear out of my presentation that once we have the technology ready, we really have to see how that we upscale the materials further towards commercial processing. I would say yes, definitely we would be looking then forward to further research projects, but also let's say collaborate together with the partners who really want to develop and do the invest into the production machinery.
Yep. From our point of view, from the point of view of the modeling tools that I showed, I think we've embraced using open source and open data approaches. Partly because it doesn't make a whole lot of sense to reinvent the wheel. If in every project, every model is redeveloped every time, that's a lot of wasted effort. And so by contributing to kind of common standards, we can build up a robust foundation and raise the level of science across the board and provide a common platform for industry to build on.
Yeah, what I would maybe just add to what you already said is that there might also be the opportunity for some smaller bilateral projects or trilateral projects to really help specific partners to bring their technologies to market. But yeah, we are also very much looking forward to large follow-up projects, with the Intelligent project being one example of those follow-up projects. I think next year there's going to be another call on Generation 3B batteries, and I'm pretty sure that some of the coordinators of the LCBAT 5 project have also plans to contribute to that plan. So yeah, we are very happy with the current funding landscape, let's say, in Europe. I mean, I think it's quite rich. It's probably not going to stay like this forever, but at the moment, it's very good. Thank you.
Yes, so regarding more specifically modeling, we feel that at each time we go to another subject, we just scratch the surface because there are so many things to study. As you said, some more specific projects are are still ongoing, because when you look at the materials, there are specific behaviors that you need to take into account. So you need to study specifically the material that you want to study to implement. We need to build it, you need to study it, you need to model it, you need to integrate it. So there are many things to be done. And for follow-up projects, when we look at modeling, for instance, you can do modeling at each scale. If you want to design material, if you want to design batteries, if you want to design manufacturing material, if you want to integrate the batteries and so on. And that's a new scope every time, a new scope for modeling, for choosing the hypothesis that you want to do, and so on. And yeah, it's a lot of work to be done still now for these technologies.
Thank you for the questions. So please, Anwar, here in the, thank you, on the other side. Great.
Yeah, thank you for great presentation. So my name is Anwar Anyas. I'm a researcher at RISE, Sweden. One of the thing actually quite interesting is that Simon, you presented very nice collaboration between the all project that is funded on the same code, and synergy seems to be very good. So I would like to ask your experience, how do you manage to collaborate between those projects? Because I'm also coordinating two projects, European project, Palestine and Novok, and we are struggling a little bit to figure out the framework, how we should collaborate. It will be very nice if you can tell us a little bit like what kind of agreement between the project you have and how you manage to collaborate. Thank you.
Sure, yeah. Yeah, thank you for the question. So as Ruben and I both highlighted, we've been having common workshops on topics that are at least scientifically of interest. And one of the big challenges in Generation 3B batteries is silicon graphite anode composites. As it was shown, silicon expands, it tends to tear up your electrodes. And from a scientific point of view, there's a lot of benefit that can be had from exchanging experiences, adhering to common standards so that when SENS publishes data and Hydra publishes data, that it's actually comparable, that we don't lose things in apples and oranges comparison. So on the one hand, we can benefit a lot from scientific discussions, but on the other hand, of course, we're working with industry. The goal is to build a European industry, and there's a lot of confidential IP. So that's one of the challenges that we face is we want to be open, but you can only be open to a point. But I think we found a good way to walk that line. Would you like to say a few words?
Yeah, I mean, just to add to that, I think it becomes easier over time. In the beginning, nothing is really in the public domain, right? Nothing is published, but if you're in the third or fourth year, papers really start to come out, right? And then it becomes, I'm sorry.
Yeah, I think because I opened the door, so maybe in the back it will be difficult to hear.
Okay, I will try to get closer to the microphone.
You can move it.
Yeah, the cable is quite short. Okay.
Don't worry.
So I think it's becoming easier with time, and maybe one other aspect that I would like to highlight is also easier if you have a partner that might have some professional help for the dissemination activities. So actually the Cobra project has a bit of the lead in our joint cluster activities, because also they have a company that they're working with that is taking care of all the outreach activities, let's say. So I think there we have some professional help and also a bit more, let's say, person power in that regard. And maybe also they have more experience with putting together newsletters, for example, which was for us quite a new thing. So that's maybe also a recommendation to look maybe for a project that has such expertise in the consortium, if possible. But I think it's highly encouraged by the European Commission to cluster up, and our experience has been really great. I mean, it's also a great networking opportunity. I mean, the projects are already quite large, the consortia, but then you're really talking about maybe around 40 different partners. coming together. So yeah, it really enhances the networking, and yeah, it has been great fun also to meet people from the other projects.
Well, I think very clear. We are just coming out of the COVID-19 pandemic. So I think all of our projects here basically have started in the midst of the COVID-19 pandemic. And I mean, it's always the same thing, yeah. You are not able to meet face to face. So for the partners who have not known each other before, that's always the case, yeah. Somebody, you know, some of the big buddies, they are writing the proposals, yeah. So the proposals and finally granted. You take your young PhD students, of course, who say, you know, please do the job, and okay, they are just you know, let's say thrown into the cold water. So and then they have to establish their network then, while you know the big bosses basically they already had it. But those ones who actually have to do the work then and have to talk to each other then all the time, they don't see each other. And I think this is something where we had to do, you know, kind of lessons learned on that. So for all of us, it was kind of new just to start in, let's say, just this virtual environment. I think this is one of the things where we really can say, okay, we have to learn still how to do this. And I mean, it's a main contributor, basically, how you overcome these things if you have some kind of consortia that already, you know, were well established before, maybe if there had been previous projects, and you know, then they continue basically on these initial connections. That's going to be working fine. But of course, if you are not able to do you know, your general assembly meetings face to face, then you're missing lots of the communication that was done. But okay, time is over. I think now we are happy to be here, and I really can say also for SUBLIME it was, you know, an eye opener. At, you know, 1 year ago when we really had our first face to face mission, and lots of the, you know, the communication which was just amongst small people, then it started to be growing, and I think that definitely helps, yeah. So hopefully we will not be having the same situation again, but I would think that next time when it would happen again, we will be better prepared anyway. So we have learned quite a lot of things, but there is nothing to be beaten by a face-to-face meeting and you know, the physical exchange, because that really brings the trust to the people and the open communication at the end.
Thank you. There's a question from Emma for Sue. Thank you.
Emma Boyac from Green Innovation. Thank you very much for your presentation and overviews. I have seen qualitative indication regarding impact, CO2 impact, but are you doing some assessment, LCA assessment for your technologies? Because when it comes to application in cars, in vehicles, it will be a means to discard or to accept the technology. And it's very important. This is first question. Second one, I have seen, unless I have missed, some indication about TRL level. I have seen in one project indicated it, Hydra, TRL6, but I haven't seen for the others. It would be possible to know it if it's done. And the last question is regarding the cost. I have seen in the first presentation, SUBLIME, indication regarding cost, and the cost towards 2030 is 75 euro per kilowatts. And is it a target or it is reachable? Thank you.
Okay, maybe I will start with SUBLIME. So first of all, SUBLIME is also targeting for TRL level 6. That's the truth. I think that was also part of the call anyway. Secondly, life cycle analysis. So since we are still evolving the technology in detail, it was already anyway planned to perform this life cycle analysis until the end of the project. So that's still, we are in, I don't know, we are month 34, I think. So that means we are still, let's say, 14 months to go for that. I think that it's going to be clear. And also, due to the volatile, cost development of the materials, also, but the actual cost impact is going to, be concerned. It comes all after we have really optimized for the upscaled materials than our concept that we can come up with a new cost estimation. So I would like to beg you a little bit for my patience until the end of the project. Yeah.
Yep, and so it seems like mechanical engineers are having a moment today, so I'm going to take a chance and fly my flag that originally I was a mechanical engineer before I moved to the battery industry. So I tend to look at things as a kind of very problem solution kind of engineer's mindset. And in Hydra, when we target this cost of the cell and how are we going to achieve it, one of our tasks was to sit down and say, okay, we want to do silicon graphite, we want to do LNMO, we want to do these manufacturing things. Which of those things are going to contribute most to getting us towards the cost target? And what we found is that by far and wide, it's the aqueous processing of the LNMO cathode material. And we've done a techno-economic LCA assessment and trying to quantify, how much that can contribute. So we're trying to develop that further to hit our overall cost target. And as part of a separate project, we were doing a look at battery manufacturing more generally and saying, in the scope of what's planned for Europe, what type of improvements do we need to make in order to have a difference? And what we found is that even if you can reduce the scrap rate at a gigafactory by just 1%, that scales to hundreds of millions of dollars. It's really incredible. So even small improvements can make a difference, and we're trying to be smart about what we target in the right order, in the right way.
Yeah, in terms of TRL, same, level 6 also came out of the call. I think level 6 basically means demonstration in a relevant environment, right? That's why we're also developing the module. And actually our module partner is even here in the audience, FPT. Which poses additional challenges, right? In terms of cost, there was also a target. I didn't mention that because I talked more about the cell level objectives, but there was a pack level target, I think, of 90 euros per kilowatt hour, which seems quite ambitious, especially on the pack level. I think the raw material cost, I mean, you mentioned that, Jens, went up a lot recently. But we've been doing a cost and scalability analysis, I mean, multiple iterations actually during the lifetime of the project. And I think our current estimate is that we are slightly above the cost target, but not like miles away, because the technology that we are working on is relatively close to the current state of the art. I mean, we're just adding silicon to the anode, and the NMC has a higher nickel content, which actually lowers costs, right? Cobalt is particularly expensive, nickel is a bit cheaper. I mean, there have been some fluctuations in the price recently, but I think that's a general tendency. And also on the electrolyte side, as we are still working mainly with a carbonate-based electrolyte, and we're just playing with additives, also here we don't see a huge change in cost. What is probably quite expensive, and I don't know, I'm not sure if that will really ever make it to commercial cells, is to really put sensors inside the cells. I mean, that requires additional manufacturing steps and probably is a bit cost prohibitive. Maybe with the exception of certain applications that require the highest level of safety, for example, but maybe not for mass market applications. So I think you really have to look at the technologies one by one and see which one can be upscaled cost effectively. And of course, we are also taking environmental factors into account. As I mentioned the cobalt before, but also graphite, natural graphite, I think is on the list of the critical raw materials. And if you go from graphite to silicon graphite with a relatively high silicon content, you can also significantly reduce a graphite amount inside the cell, which I think is also a benefit from that point of view. Yeah, I think that would be a sense perspective.
For the modeling part, I think the issue is quite different, especially regarding the TRL and so on, because we are quite, we need to have the technology in order to make sure that we are modeling the right thing in the end. But we need to be ready for the next technology. That's the whole point of this project, to make sure that what we describe is representative of the next technologies, so silicon, but other materials also high volumetric expansion or high volumetric or mechanical aspects like sulfur and something like that. And so it will create some basics for the next developments. And so there will be, it's a first demonstrator, a technology that we can test and validate. And then we will be able to use it for other technologies in order to make sure that that these new technologies like lithium sulfur or other intermetallic alloys are still valid for the next generation of batteries.
Just a very small addition. In the work program 21-22, we also had a joint topic between Bat4U and 2.0, specifically on life cycle analysis. So this aspect is also being covered from the two sides, the batteries and the vehicles. And then we also have a topic in the call, the second part of Batteries 23, that is opening in May, on the battery passport. And of course, the CO2 footprint is also going to be part of that.
Thank you for complimenting. There was a question in the 6th row. Please, thank you.
Hello, hi. This is Karim Hassan from the Catalan Agency for Businesses. I have a question for Dr. Petit and the Modalis project. The first one is, how will the toolbox look once it's mature, so to say? Will it be 100% open, and will just anybody be able to access the models, the data, and so on? And the second one is, how are the models kind of like communicating, or are you just layering them to give a more global picture, because DFT is not thermodynamics, et cetera, et cetera. So that's interesting if you could build on that. Thank you.
So yeah, the main issue with the multi-scale is that we don't have only a multi-scale behavior, but a multi-temporal behavior. When you are using DFT, where picosecond, something like that, when you are using 1D simulation, you are simulating years of behavior of the battery, and the two are not directly communicating. So what we aim at in the project is to create and understand the right indicators from the DFT in order to get the right parameters from the continuum calculations, or for the FEM calculations at particle level and so on, and then create some correlation from there using different tools, different softwares. So among the partners of the project, we have University of Torino and Siemens Industry Softwares. So they have both their own software that they are developing within the project. So University of Torino is developing Crystal code for DFT calculation of active materials specifically. And Siemens Industry Software is developing 1D simulation code, SimCenter AmSim and SimCenter Star CCM Plus. And so there will be the main output of the project as commercial softwares. So that's they are using this input, and as also as an output, they have developed a specific library for Star CCM Plus in order to design batteries directly in their tools, choosing it's based on what they done before on Battery Design Studio, in order to design and simulate batteries in 3D correctly and in a user-friendly manner. And regarding the communication between the scale, so it's not completely integrated. It's not possible to completely integrate that, because it's when you do DFT and so on, you need a cluster and very big calculation means. When you do 1D simulation, you can use a regular computer, so it's not completely compatible. So the aim is to have specific methodologies from DFT. Once your colleagues who are when the teams that are used to do ab initio modeling have done the calculation, you can use and communicate. That's a big difficulty we have, and we talked about COVID. It was also some issue with us in order to make a good communication between teams. When I talk to a colleague from ab initio, I'm not able to understand exactly what they want to say to me regarding diffusion parameters. They are far away from what I used to have and what I measure at the test bench and so on. So as I said, there are some improvement to be done because we scratch the surface. We have a mean to calculate diffusion coefficient. We have 2 orders of magnitude. We know that the material is not perfect, so we need to understand how we link this huge range of diffusion coefficient with the actual diffusion coefficient we need to use in our model in 1D simulation. And it's still something that needs to be done after our Modelis project.
Thank you. There was a question from Appenzeller. No, yes, there, Appenzeller.
Thank you so much. My name is Johan Blondelle. Thank you very much for your presentation. Really good results and promising results. And my question is now, you have clear at the beginning treated and investigated how are the competition worldwide in this direction. And now my question is, if you are looking today in this direction, what do you see is a competition in US, in China, Japan, in the direction of research results that we here in Europe, you are 4 representatives of this one, equal or higher, or we had to do a next step to reach this level? That would be my question. Thank you.
Very hard, please. Someone wants to reply? For sure we can say that we are the best in research.
Okay, of course, if we say this all the time, then we start to believe this, and at the end, then we think then we don't have to further, let's say, develop. I think that would be maybe a little bit dangerous to think that. But I personally think also during the experience that might, since I'm coordinating SUBLIME, is basically all the research at the end needs a good foundation by providing materials tools from the industry. And of course, what the delivery of materials is concerned, I'm getting a little bit repetitive maybe on this because I said this already before. We need to keep up. So because all the materials that we need in order to do our laboratory experiments, they should come from Europe, and we should not rely on getting them from wherever the place is, Asia or see this. We had delays, for example, in materials delivery just because of the COVID-19 pandemic and all what was basically then the consequence of this. And that's something, of course, that is bringing us behind. But what we see, of course, that we do in terms of the other research are really on a very high level and really on the edge. But of course, there is no help if you at the end then have to wait for the lab materials to continue with your research.
Yep. I think I would have given you 2 different answers before and after the Inflation Reduction Act. In the time since, there's clearly been a lot of movement on building battery industry in the U.S. Even the Norwegian gigafactories are starting to open U.S.-based factories. So there's been a lot of movement on the industry side of things. But I think in terms of research, there's nothing really going on in the United States at the same level as what's being done in Europe, especially these kind of large flagship type projects like Battery 2030 and Big Map. They're often spoken about with some enviousness, I think, with some of my American colleagues. And this is something that I think Europe is doing really well and something that's unique in the world, and has given us a kind of competitive advantage in research at the moment. That being said, I think the United States has been kind of late to the party on battery research, but they're starting to show up now. So you know, just because we've done well in the past doesn't mean we can you know, rest easy. We need to continue striving to be the best if we want to maintain that competitive edge.
Yeah, it's a difficult topic, right? It's quite political, I think. Yeah, I think we should really continue to strive for excellence in research. I mean, my feeling is almost a bit different than yours, Simon. I feel like that many of the most innovative works still come out of the US in terms of scientific publication, right? I mean, they have also very, very good groups, I think, that are working at the leading edge. So I think we cannot we cannot slow down. We rather have to speed up. I mean, it also happened to us a few times that we got scooped because they are sometimes very efficient at really finalizing a manuscript and bringing it out. And another aspect that I would like to discuss here is maybe the topic of IP generation. I'm also wondering if we could put a larger emphasis, maybe also from the Commission, on IP generation, because that's, I think, really, really important for the European economy, right, and for European companies and for our financial well-being, let's say, right? I mean, publications are probably not enough. In the end, we also really need to develop new IP. And from what I heard, for example, from China, is that there, I think the funding agencies are sometimes putting a larger emphasis on IP generation, on patents and so on, than maybe here in Europe. And maybe that's something that more for the Commission also to stress a bit more in future calls. But it depends, of course, a lot also on the TRL level, right? And I guess there's not one solution for all calls, but that's a little bit my feeling. But we for sure have also really cutting edge research infrastructure in Europe. If I think about beamlines, for example, I mean, for very fundamental research, I think we are very well equipped. But yeah, I mean, there's also a lot of competition in the world, also from Asia, not only from the US. So I think we have to do our best.
Yeah, the competition, as you said, is very important in worldwide. But what we have also, I think what we could rely on is the network that we have in Europe. Especially, we have all the skills needed for that. We have good material manufacturers. We have good material providers from Europe. We have also battery manufacturers, battery integrators, OEMs, and so on for a large range of applications. And all this helps us to create this collaboration that needs to be done in order to efficiently create and get the edge for the industry. It's not just having the best material that will help us to prevail, or having the best integration, having the best car. We need to have the best material integrated in the best battery, integrated in the best car, and so on. And for that, you need a good collaboration between all stakeholders for that.
Just while you are thinking to next question, I want just to add that this also a good collaboration between, let me say, the European Commission and the main groups working like Batteries Europe, BEPA, and Battery 2030 brought to get these calls. So this is something that is not starting from the scratch, but is a discussion, very wide discussion between people. So I really push you to be part of the expert groups that are working within these projects. So participate, and then help. Everyone is writing this call to do the best and get the best way to get projects funded. Not funded, this is up to the evaluators, but the calls that are pushing to get great results in Europe, first of all, and reach and overcome the competition. Is there some further questions? Please, Pietro, there. Question from Pietro was missing, so.
Yes, I am used to make questions, yes. I remember I was participating at the very first European project on batteries in Darmstadt, and there was a session on nanotechnologies for batteries, okay? And I raised up, again, I asked a question, it says, if there is a nanowire on silicon, although I am an old theoretical physicist, I can still calculate what is the energy needed to expand this single nanowire, okay? Now, to my friend Martin, and also the other, I see here that all these simulations are by mechanical engineers or engineers in general. So, in my perspective, is the electrochemistry is very, very complex at a nano level. I still haven't seen nothing or very little First, because you never know exactly how the electrolyte is, or then. So my opinion is that there is a need to understand the battery more at the physical level. And by the way, take the provocation. I know people working for pure physical batteries. Ciao electrochemistry. Remember my starting point. Tell me what sort of nanowires you are using, and although I am an old theoretical physicist, I can still make some calculation on the energy needed to absorb and to release energy from a single nanowire. I know groups working on pure physical batteries. And I agree with what Joseph was saying. We need more knowledge at the physical level, or also at the theoretical chemistry level, to take a real advantage. Until we simulate from a pure engineering point of view, I don't see any real step that can put us in advantage with the Chinese. Martin, please excuse me if I was working for a while, but we remain at an engineering level. I'm sorry from this point of view. I have to emphasize this aspect, okay? But perhaps your point of view, you are in the field more. I'm not in the battery environment anymore. I'm thinking about something else. Perhaps you can contradict me and say, no, at a pure theoretical level, we are engaging theoretical physicists and theoretical chemists to better understand what we are doing. Perhaps please contradict me. But I don't see this in the roadmap as well.
There is I think there is a huge gap between the expectation from the people who are working with batteries and what we can do actually, especially at the theoretical point of view, because theoretical point of view gives us a lot of information on how the battery works, what would be the best material and so on, and you can design a material. But when you put it together with collector, with binders, with separator, with the other electrode, with material that's evolving a long time and so on, everything is fucked and you cannot get anything working at all compared to what you have in theory. And that's the main issue we have with theory, because no material is perfect. You take NMC, is not a perfect NMC crystal that you have, and you have a diffusion from one point to another. The lithium diffusion is not from one part of the NMC to the other. There are different paths of diffusion with different diffusion coefficient and so on. And how do you derive a diffusion coefficient that is good for using into a battery in a car when you don't know where the lithium comes from, where it goes from site to site and so on? It's very complicated. And that's why I said earlier, we just scratched this from Modalis, for instance. We spend a lot of time to create the crystal, to create crystals that are stable. When you remove cobalt, my colleagues from University of Torino, Gemate and CRF, lost a lot of airs. If you know Maurus Groy, he has no air at all now. But it was very complicated to do that, because you need to have bigger and bigger cells to model, and so you need bigger and bigger computational. It has a bigger and bigger computational cost, and it has less and less representativity because it's too perfect. The material, it's cut, it's grinded, you have, it evolves, you lose manganese, you lose particles, you have CEI and so on. You have so much things that are changing your material that what you calculate by theory is completely different from what you have. So, and when you talk to car manufacturers, they say, okay, we have a material, we have NMC, we have bought them from Umicore, we have bought them for I don't know which manufacturer, we put them into the battery, how does the battery work? But if you ask for your colleagues from DFT, okay, what is the material the material working? How the material is working? If you have an MC, and they say, okay, we have so much EV of something working, and I don't know, but we won't be able to have the polarization curve. You won't be able to have the voltage of your battery. You'll be able to have the resistance of your battery directly. So you need to find a way to close the gap. So it's a huge part of the work of Modalis and many other projects in order to create these bridges between the scales. It's very complicated. And also you need to find other ways to evaluate these quantities, and this goes by specific experiments, of course, and you lose the theoretical chemistry from this because you need to have real parameters, real behavior, and not only theory. That's a big difficulty for the modeling part.
Okay. Do you want to reply, for example, with experience of big projects like Big Map or something?
Yep.
And then we have just one additional question and we close the session.
Okay. Yeah, well, I think it's a really good point that you bring up, actually, and I wouldn't say that we need only physics-based and really theoretically sound models. We need them in addition to the more engineering related models. Because on the one hand, there's a lot of really excellent theorists doing DFT simulations and molecular dynamics and FCI QMC, and a lot of really fancy theoretically grounded physics-based modeling methods. And they can screen a lot of materials and provide you with a lot of opportunities that could work. But as we said, as soon as you try to build it into a cell, it's a whole new can of worms that you're opening. So you need, on the one hand, theorists to do the kind of screening calculations and to say, okay, this is what's possible. But then you also need the engineers to come along and say, okay, well, this is how we put it into a real cell. And on the other hand, with engineers, we like to fit things, and John von Neumann famously said, give me 5 parameters and I'll fit you an elephant, and give me 6 and I'll make him wiggle his trunk, right? So, fitting in empirical models helps, but also as engineers, we need to have this mindset that our models are only as valuable as the knowledge that they represent. They have to be grounded in physics, and they have to reflect physical reality. So I think it's a good point, and I think we need to try to do more to bring those two communities together and get the electrochemists and the engineers talking together.
Maybe I would like to bring the third group into the play. So actually, my background is, as I said, I'm a mechanical engineer. So and I have lots of background experience in modeling of turbine combustion. And every time when I see all these presentations, also within SUBLIME, by the way, which I didn't show, but I will show once they have completed the modeling, that the highly dimensionality of the problems, they come very clear to the challenges that we had when we tried to model turbulence. So it means, you have the 3 dimensions, then you have the microscope, which is actually the 4th dimension. And I tell you, my recommendation is just talk to these guys, maybe, because they already have, the tools how to abstract things, because it's getting almost the same complexity as you might have, and they might have some other ideas. And I think there could be lots of synergies, and these things, as we know, probably all these models of turbine combustion, they might get unemployed. I don't know at some time, but maybe they find another employment because they could bring some new ideas into that, and that could be of benefit. So there are some keywords, like flame rate theory, which try to always to reduce the dimensionality of the problems. Always when I see these things, when you try to model microscale, I thought, oh, that looks like a flamelet, whatever, yeah. So, I mean, they have some kind of these tools at hand. They're just named differently, maybe.
Okay, so I guess time is over. So I'm sure that you will find additional time for questions during the coffee break, so a networking time. So I want to thank you all, maybe for this very interesting session. And please, Johan, if you want to...
Yes, just some housekeeping for your information. So you can go down for the coffee and a drink, of course, but don't forget to also visit the exhibition area. At the European Commission stand. You can also get in touch with the new projects that are just starting under Horizon Europe, also from the battery call. So it's a good opportunity to take stock of what will be happening. I just inform you that we restart at 4:30 in this room here. We have a session on next generation electrified vehicles optimized for infrastructure, and there is a CCAM session in the Einstein room. So thank you very much once again to all of the speakers and to you for your attention.